You've probably been taught the scientific method many times before, but I'm going to teach it to you in a slightly different way that's much more applicable to chemistry and to the science world in general. All right? So I'm going to give you the traditional background on the scientific method here on this video, but you're going to have an assignment after this where you're going to analyze a scientific text, and in that scientific text, you're going to highlight for me each piece of the scientific method as it's being used within that scientific article. All right, so probably for one of the first times in your life, you're actually going to use this for real with real scientific data. The scientific method has multiple steps, and really depending on the teacher and the textbook, they might be worded slightly differently. But for me, the first step, and this is always the first step, by the way, is to simply ask a question. The scientific method starts when you ask a question about something. That is how, what, when, who, which, why, or where, right? Simply asking a question. So I have a sample. Why won't my car start? Right? Now I would tell you that if you had a Chevy, that's probably, you're probably done, and that's why. I'm just kidding. But anyway, so that's an example. Why won't my car start? You've asked a question. The second step is to do background research. Rather than starting from scratch and putting together a plan, you might want to do some research, right? In other words, you're not just jumping into a new project blind. You've got some knowledge, you've got some information in your tool belt that'll help you that will lead you to the truth. All right? So, researching, an example would be, why won't my car start? And for background research, maybe doing some research to check ways to determine whether or not your battery is dead or whether or not your battery is bad, right? After you do background research, you see on the little diagram, the next step is to construct a hypothesis, right? Now, the definition of a hypothesis, you know it as an educated guess. There are some people now that would say that is too easy or too broad of a definition, but we're going to roll with it because why not? Look, a hypothesis is just a thought or a guess, and you're essentially going to run each of the following steps of the scientific method on your hypothesis to test it and see whether or not it's accurate or not, right? So call it what you want. It's an attempt to answer your question with an explanation that can be tested. In other words, proven factual, right? And by the way, if your hypothesis is proven to be wrong, that's just as useful as proving it to be right. Trust me, guys, you never, ever, ever design an experiment in a way where you try to prove your hypothesis correct, because that's injecting bias, right? You want it to come out truthful. If your hypothesis comes out rejected as a result of the scientific method, well, great. That just means you're digging for facts. A good hypothesis allows you to make a prediction, right? So you've asked a question, why won't my car start? The background research, maybe let's look up some information to see, what constitutes a genuinely dead battery, right? The hypothesis, usually an if-then statement, by the way. If I charge my battery, then my car will start. In other words, my hypothesis is I do have a dead battery after doing the background research, and I feel like I can test this hypothesis by hooking it up to a charger, giving it some time, and see if it starts after that. Right? And as you can see, the next step is to test your hypothesis, right? Testing your hypothesis is simply hooking up your battery to a charger and trying to start it in a little while, right? Your experiment tests whether your prediction or whether or not your hypothesis is accurate, right? So if your hypothesis is supported, great. If it's not, that's also great. But you have to start all over again, as you see here on this diagram, right? Which is, again, experiments, labs in science, they're not always cut and dry. I did a bunch of labs in college where it took, multiple hours. I'm talking 5, 6, some even a couple days, and you had to go different times of the day and night to check on the experiment, right? It is important for it to be a fair test. Again, never design an experiment to just try to prove your hypothesis. All right? So after you perform the test, you got to see if your procedure is working, right? Now, if your procedure does work, great. You can analyze data and draw conclusions and kind of wrap everything up. If it doesn't work, you troubleshoot and you pretty much, start over again. But say it does work. You analyze your data and you draw conclusions. Once your experiment is complete, you collect your measurements and analyze them to see if it supports your hypothesis, right? So the car started. That means your hypothesis was correct. It means that you had a bad battery. You performed the proper test to see if to determine if your hypothesis was true or not. And it turns out your hypothesis was right. But again, as you see here, if your procedure works, and when you analyze and draw conclusions, if your results do not align with the hypothesis or only partially align with the hypothesis, you start back over. You form a new hypothesis. All right? And this is all common sense for the most part. It's just in a graphical form. All right. So if everything's good to go, you've validated your hypothesis, everything's clear, you communicate your results. Professional scientists publish their final report in a scientific journal, or they present their information at a conference or at a meeting or, just something like that. And you have journals, right? Academic journals from the American Chemical Society and a bunch of other places, right, where you report this factual information. And trust me, they vet the information to be sure it's factual. And to prevent you from just spamming their website with false information, they make you pay to submit your article. So you're not going to pay to submit fake stuff, right? So let me be very clear here. You test with an experiment. You determine whether or not your procedure is working. If your procedure isn't working, it doesn't necessarily mean your hypothesis is wrong. It may mean that you have a flaw in one of the steps of your experiment. So you might go back and tweak that. But if your procedure is working, and after you analyze data and draw conclusions, if you find that the data is just not backing up your hypothesis, that's when you pretty much start all over again, right? Just to be very clear. Now, in my few years of teaching high school, I've never had a student get this right. They think they know it, but frankly, they just, hate to say it, but haven't always been taught correctly on this. Or fully explained, we'll put it that way. There's a difference between a scientific law and a scientific theory, all right? Let's just go ahead and delve into it. Here's the definition of a scientific law. It is a concise statement that summarizes the results of many observations and experiments. In other words, guys, you conducted the same experiment, say 100 times. The data that you collected always was similar, and you used that data from those 100 trials to summarize the results. Nowhere in this definition does it say it explains the reason why the phenomena occurred. A scientific law simply summarizes the results after you conduct the same experiment many, many times and you get coincide repeating data. It's a rule that describes some sort of a pattern in nature, right? So in other words, a scientific law is supported by years of experimentation and evidence, and all it does is summarizes the results of all those years of experimentation and the data that was collected as a result. A scientific law summarizes the results. It does not explain why. The explaining why it happened the way it did is up to the science, or is what a scientific theory is. The scientific theory is the explanation for the observations that you concisely state during for a scientific law. So a law is simply a summary of the results of many observations, and the theory is the explanation or the reason why you got that data. Okay? So I'm going to go whatever on this, whatever. I got a chart here that's just great. Okay? Now, a theory and a law, they do have things in common. They're based on the scientific method. They can be used to make predictions. They can be revised. I often hear, well, Mr. Johnson, a law is set in stone. It cannot be changed. And my counter to that usually is, well, in government, you can change a law through legislation, right? It's the same thing in science. A scientific law is not absolute, right? It can be changed. So, a law is a summary of a set of observations after you've been watching something, for a long time, and you've done a bunch of experiments on it. The theory explains why what you observed in the law happened. All right? So that's the difference between a scientific law and a scientific theory. It has nothing to do with, it can never be changed, blah, 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 blah. All right? So that, my friends, is the scientific method, and I hope you enjoyed the assignment coming up. You might want to replay this video while you're doing it because I want you to critically analyze that scientific text so you can accurately highlight and show all of the steps of the scientific method within that article.